Welcome back. In this video, we'll be exploring how to measure how well the line fits our data in the context of simple linear regression. Here's our learning objectives. At the end of the video, make sure that you're familiar with all of these concepts. All right, so there's going to be two main ways that we measure how well our line fits the data. That is, how good are the predictions for y that we might make based on x. So those two measures are what we call the coefficient of determination, or R squared, and the standard deviation of the errors, S sub E. So two different ways, but both getting at the same thing, which is, how good is the fit? All right, so think back to ANOVA. So in ANOVA, we thought about, there's some total amount of variation for some variable, such as, what's the distance that cars can stop? And then we took that variation and we split it into two parts. The parts that were explained, and in ANOVA, suppose we explained how far it took for a car to stop based on what type of car it was. So that would be explained. And then the leftover variation was the part that we couldn't explain. So we called that error or maybe residual. So we're going to do pretty much the same thing here. We're going to take the total variation in our y variable and split it into two parts. The explained, which for our regression model we'll call the model, and the unexplained, which we can call error or residual. All right, so we're going to, as we did in ANOVA, be able to quantify that variation with sums of squares. So let's start with the total sum of squares. So I just have it color-coded in the blue here. So the total sum of squares is going to look at how far away was the actual y value for an individual. So this is our gas station data again. So this is one single gas station. Its actual sales looks like it's around 12,000 gallons. Well, how far away was that from the average y value? Which there's a bar here. It's a little under 8,000. All right, so that deviation symbolically is the yi minus y bar. So y bar is just the average y. Okay, so all these guys here would have positive deviations because they're above the green line. And all these guys here would have negative deviations because they're below the green line. Okay, and the size of the deviation tells us by how much. Okay, so if we wanted to measure just the total variability, how much do sales tend to vary in general, not even worrying about the traffic volume, we could compute this sum of squares by finding that deviation for every single gas station, squaring them individually, and then adding them up. So that'd be the sum of squares total. All right. Next, let's think about the sum of squares for the model. That is, what does the incorporation of this relationship with traffic volume help to explain? So for that, we're going to use the sample regression line, which is the red line. And we saw in the last video that at any value of x, at least if we stay on the graph here, for any value of x, we could plug x into the sample regression line and predict the value of y. And our predicted value was denoted with the hat. Okay, so if we think about what we did on the last slide, we were comparing to the sample mean for y. But now we're going to compare to the predicted value for y. Compare that to the average. Okay, so that's going to span this distance here. Now note, for all these, scratch that idea, but this is going to help essentially measure that, well, in this case, we notice a general tendency for the points on the right-hand side of the graph to be above the green line and the points on the left-hand side of the graph to be below the green line. So that this flat slope of the green line is not as good a fit as this positive slope that we have here for this data set. All right, so same idea as before. The deviation will be calculated, just this time it's between the predicted value and the average value for y. Do that for every single gas station, square the deviations before adding them up. All right, and then the last part, the error, that we've seen before. That was in the last video. So we were asking, well, how far off were we from the line? And thinking about just the vertical distance. So remember, that was the actual y value minus the predicted. So if we're still focusing on this top right gas station, it's going to have a positive deviation. It exceeded the sales we would have predicted based on its traffic. And then that deviation would get squared. Do the same for all the others and add it up. Okay, and the sums of squares, like in ANOVA, are additive. So the total sum of squares is going to split into two parts, which will simply add up, the model and the error. So if we have a really good fit, we should have a small error, meaning the points are really close to the line. And since the two parts have to add up to the total, that would mean that the sum of squares model is relatively large. Okay. So if the model is a lot larger than the error, we'd have a good fit. Whereas if the error was large and the model was low, we'd have a poor fit. Okay, so how to standardize that to be able to handle any situation that's thrown at us. We're going to change those sum of squares into what we call the coefficient of determination. Most likely you've heard of it before, called R squared. So R squared is going to be standardized to be a proportion. It's the proportion of the total variation in y that's explained by the regression model. So we could calculate this one of two ways. We could either sort of do it directly if we want to see what proportion is explained. We'd have the explained over the total. Or we could think about, let's assume we start with explaining everything, start with a proportion of 1, which is like 100%, and then subtract out the fraction that's unexplained. So remember, the error was the unexplained. So what fraction of the total is that? All right, since this is a proportion, all proportions we know have to be between 0 and 1. So R squared is no different. It's going to lie on that spectrum. So an R squared of 0 means that the model explains nothing. That X does not help predict Y at all. At the other extreme, an R squared of 1 means that we can make perfect predictions. That if we know X, we put it into our equation, we predict Y with absolute certainty. Now, with a real life data set, I've never actually seen one of those happen, but it's a spectrum. So are we closer to 0 or are we closer to 1? It should also be noted that R squared mathematically will also turn out to be simply the correlation coefficient raised to the second power. Or if you want to go backwards, you could take the square root. With the caveat, be careful, if your scatter plot has a decreasing trend, you would need to take the negative square root if you're trying to get to the correlation coefficient. Okay. So R squared here, it's related to the correlation coefficient, but be careful, they have very different interpretations. And R squared here by itself is not going to tell us the direction of the relationship. So we could have a strong negative or a strong positive. If the strength is the same, they would have the same R squared. All right, so R squared is automatically produced whenever you fit Y by X and add a regression line. So we did that last time. We discussed the sample regression equation last time. And then under the summary of fit, the first item there is R squared. So that's our coefficient of determination. So the proportion is given, what proportion of the variation in sales is explained or predicted by the traffic volume. A lot of people prefer working with percentages, just more, commonly used in everyday life. So if you like, you can multiply that proportion by 100%. And usually I'll round off to the nearest 1/10 of a percent. So here, R square of 0.5485 0.6596. I'll multiply by 100%, round off, and say that about 54.9% of the variability in sales is explained by the traffic volume. Okay, so we're explaining the variability in Y based on what we know about X. Now, we can use the word explained or predicted by the traffic volume. Just be careful, though, it's still not known that this is cause and effect. And for these gas stations, unless we controlled for all the other variables, like, how clean is the gas station? How friendly are the staff? All those things could also affect the sales, aside from the traffic volume. All right, so I'd like you to pause the video and try to come up with a one-sentence interpretation of R squared for the muscle data. So remember, X was the age of middle-aged and elderly men in years, and Y was the lean muscle mass in pounds. All right, so if we convert to a percentage, that would be about 67.9% of the variation in the lean muscle mass is explained or predicted by the age in years. I just want to highlight that this calculation is just based on this sample of men. So just among these guys here, that's the predictive power that we have. How much, to what extent can we predict their muscle mass based on their age? If we rounded up a different group of men and measured them, in all likelihood, R squared would change, maybe a little, maybe a lot. All right, so the other way we might measure the fit of our line is by seeing, well, typically how far off are the points from the line? And when we think how far off, we're thinking in the vertical direction only, so just for Y. So this quantity is denoted S sub E, and it goes by a few names. Some call it the standard error of the estimate. Some call it the standard deviation of the errors. I like that name because, reading the symbols, that's what it looks like to me. We've got little s for sample standard deviation and then E for error. So the sample standard deviation of the errors. And then what JMP's going to call it is the root mean square error. So sound familiar? We saw the root mean square error in ANOVA. So it's the same sort of thing here. We're going to take the square root of the mean square error. So the mean square error, remember, is the sum of squares for error divided by the degrees of freedom for error. And it's just, we'll explain why later, but the degrees of freedom for the error in regression are going to be n minus 2. Okay, if you want to know, you don't, but I'll tell you anyway. The minus 2 is because when we ultimately think about the population regression line, there's two parameters involved, the population slope and the population y-intercept. So because there's two variables, two parameters, that's why we have the minus 2 for the degrees of freedom. All right, so this will also be produced automatically. So it's just 2 rows below the R square. You might be curious about this R squared adjusted. That will be important for multiple regression, which is after the midterm. So we'll talk about that then, but we're not going to use it for simple linear regression. So skip on down to the root mean square error. And here it's about 1.5. So that's typically, how far away are the points up or down from the line. So to give that some context, well, that's, at least for this sample, how far off were the actual sales for a gas station compared to the predicted values, which were made using the traffic. Okay, so typically how far off or how far away were the actual sales from the predicted sales with those predictions being made based on the traffic. Another note, if the root mean square error wasn't shown, so suppose it was just cropped off or missing, you could go to the ANOVA table and find the mean square error and just take the square root of that. Okay, so your turn. Pause the video and see if you can come up with a one-sentence interpretation of the root mean square error for the muscle data set. All right, so for this sample of men, middle-aged and elderly only, the actual lean muscle mass that they had was typically about 8.3 pounds away from the predictions we would have made based on their age. Okay, so this root mean square error will be measured in the same units as the y variable because we're measuring the typical deviation in y from what was predicted. Okay. So that's it. So you'll need to be able to find R squared and S sub E for a given data set. Relate those to the sums of squares. Calculate them if you have just the sum of squares available. And then most importantly, I think, is come up with interpretations in context. So pay close attention to which variable is it that we're describing. For instance, we're trying to explain the variability in the y variable, and then also relate it to the units that were measured. So for instance, S sub E, are we measuring the typical error in dollars or in pounds or in gallons of gas? Be sure to provide some context there. All right, so if you watched, hopefully you watched these in order, the correlation video, then the sample regression line, and then the measuring fit, then you are ready for homework 8. It is on Blackboard, and it's to be submitted by Blackboard, and it's due by 8 a.m. on Thursday, April 2nd. Although, of course, if you watched all 3 videos, you're ready now, you could turn it in early. Okay. All right, I'll see you next week.